Welcome to this explainer from Forge College. So in our previous lesson, evaluating performance metrics for Cloudbreak, we explored Cloudbreak's absolutely mind-blowing read performance and throughput within the Solana ecosystem. But here's the harsh reality of systems engineering. All those incredible IOPS and zero latency cache hits, yeah, they literally do not matter if your server is on fire. Today, we're diving into the true engineer's blueprint for keeping things running when things inevitably go wrong. Let's get into it.
Think of me as your senior architect today. Here's our schematic. We're going to cover the reality of downtime, core reliability concepts, mitigating failure modes, the recovery workflow, automating failover logic, and finally, scaling with confidence.
All right, starting with Section 1, the reality of downtime, when things break.
Here is a universal engineering truth you're going to learn sooner or later. Everything eventually breaks. Hardware degrades, networks partition, and honestly, by the sheer laws of the universe, it usually happens at 3 a.m. when you are fast asleep and your pager just starts screaming. So this raises an absolutely crucial question for us. Given the massive Cloudbreak performance advantages we just evaluated in the last lesson, how reliably do they actually hold up under partial failures? Basically, how do we protect those massive throughput and latency gains when operational chaos strikes?
Moving to Section 2, core reliability concepts. Are reliability blocks.
To survive catastrophic failures in production, we need to design our systems a lot like the watertight compartments of a submarine. You know, if one section of the hull floods, the entire ship shouldn't sink right along with it. We need compartmentalized resilience. And this brings us to failure isolation. This is all about confining faults to a specific subset of accounts or shards, rather than letting those errors just cascade across the whole ledger. By leveraging Cloudbreak's specific account storage layout, we're essentially minimizing the dreaded blast radius of any given crash. If one node goes down, it only takes a tiny, isolated fraction of the system with it.
Cloudbreak achieves this isolation through 3 really elegant mechanisms. First up, locality of state. This dramatically reduces the number of dependencies a single request has to touch. Second, independent replication domains, which prevents a correlated loss across multiple nodes. And third, the containment of write paths. This one's a game changer because it stops a blocked write path from impacting completely unrelated read requests. Cloudbreak's architecture just inherently protects your system from that devastating domino effect.
But look, isolation alone isn't enough. We also need strategic redundancy. Here we see 2 competing architectural plans. On one hand, synchronous replication gives you incredibly low data loss, but it hits you hard with high write latency. On the flip side, asynchronous replication gives you that beautiful, snappy, low write latency, but it makes your recovery process way more complex. The trick here is choosing your trade-offs wisely based on your specific dataset. And remember, because Cloudbreak uses aggressive local caching, your read availability actually stays remarkably high even during a partial write path outage, which is pretty awesome.
On to Section 3, mitigating failure modes. Let's get into some hands-on troubleshooting.
So what actually happens when the red lights start flashing and things go fundamentally wrong? Think of this table as your ultimate survival matrix. Look at how each disaster scenario is countered directly by a Cloudbreak feature. Got a node crash? Well, Cloudbreak's localized partitions mean you just promote a warm standby and rehydrate the state. Dealing with a network partition? Those independent replication domains allow you to route reads locally while temporarily holding off or quiescing your writes. What about cache corruption? The cache-friendly layout means you can just invalidate the cache and temporarily degrade to direct reads without taking the entire system offline. It's a highly methodical, targeted defense strategy.
Section 4. The recovery workflow. Your emergency action plan.
As any senior engineer will quickly tell you, hope is not a strategy. We need a concrete action plan with strict time budgets for when a node fails under peak load. Here is the exact operational sequence you need. First, detect the failure using automated probes tracking latency and errors. Second, isolate the traffic away from the blast radius. Third, route read-heavy traffic to healthy caches. Fourth, recover by rebuilding or replacing the node. And finally, validate the data invariants before gradually sending traffic back. Now, the secret sauce that speeds up that recover phase in Cloudbreak is keeping state checkpoints readily accessible. We call this state rehydration, and replaying those checkpoints is an absolute massive time saver for your mean time to repair.
Of course, nothing in distributed systems comes for free, right? We face a classic DevOps nightmare here, the trade-off of automatic failover. Yes, an aggressive automatic failover drastically reduces your mean time to repair. It gets you back online incredibly fast. But if it misfires or overreacts, you risk a split-brain scenario. That's where two separate parts of your system both think they are the authoritative single source of truth. It's a really delicate and sometimes terrifying balance between the speed of recovery and absolute data correctness.
Section 5. Automating failover logic. Using health checks.
So how do we manage that delicate balance without actually having to wake up at 3 a.m. to make manual decisions? We have to move up to the control plane and completely automate this workflow using health check aggregators. Here are the vital tuning knobs drawn straight from our system blueprints: your probe interval, your latency threshold, and your error threshold. And here is my very serious warning to the newer builders out there. Do not set your error_threshold too low, because Cloudbreak keeps so many reads local and cached, you might just see a transient latency spike that completely resolves itself. If your threshold is too sensitive, you're going to trigger massive, cascading failovers for a minor hiccup that would have literally cleared up in milliseconds.
Finally, Section 6, Scaling with Confidence, Getting to Production Readiness. Let's bring this entire schematic together. You must isolate failures to reduce the blast radius. You use strategic redundancy and state rehydration to restore capacity quickly, and you carefully combine both infrastructure and store-specific signals to perfectly tune that failover logic. It's a complete ecosystem approach to reliability.
I really want you to burn this golden rule into your mind. Map account classes to recovery SLAs, your strict agreements on uptime and speed. Pick replication strategies, and implement explicit monitoring gates. This is the ultimate takeaway for intermediate Solana builders preparing for the real world. You don't just guess, you map your data, you plan your architecture, and you strictly monitor your boundaries.
So, I'm going to leave you with this provocative thought to chew on as we wrap up this explainer. Look at your own Web3 applications right now. What are your most latency-sensitive account types, and do you actually know what their current error rate metrics are? Because if you don't, well, consider that your homework before our next session where we tackle scaling use cases. To dive much deeper into this subject and explore a wealth of other Web3-related topics, be sure to visit Forge College. Keep building resilient systems, go map those SLAs, and I'll see you in the next explainer.